let me start by challenging Frank, because we always need something to disagree on, otherwise science stops. And it's getting more and more difficult to find stuff to disagree on, that's the problem. But at least...
You don't speak in the microphone.
Oh, sorry. Okay, sorry. So as long as... you said in the beginning that publishing should follow science, you know? And I think it has been the other way around. Science has been kept in a deadly embrace by publishing. The stupid journal impact factor and all this stuff. We have to publish in papers, burying our results, as we know. So I think we hopefully flip today to publishing following the scientific need and not the other way around, okay? So that sounds like more logical to me. So let's first start with the hourglass. Of course, this is already interoperability, the eye of FAIR. I made the slide in Keynote, and of course, PowerPoint decides to remove something, that's okay. But we heard already about GoFair from Eric and the center of the hourglass, and it's really important to understand that we only want to impose this absolutely minimal standard, what we call a machine-actionable unit of information. And Tobias showed the nanopublication anatomy, as it was, I think Jan and I published this first in 2009 or so. And then Paul Groth and others, I think Tobias already, the anatomy of a nanopublication, so it's already there for quite some time. And then Tobias became indeed the master of it. But that's all we ask. If all objects in the internet are machine-actionable units of information, or FAIR digital objects, there's another, it's a brand name for that, then both in applications and orchestration, as Eric showed, you can do anything you want. We don't impose any technology on it. And what I would like to emphasize for Eric's talk again is that in the last 5 or 6 years implementing FAIR, we found out that making explicit which choices you made, which identifiers you use for what, is even more important than which choices you make. Because the computer doesn't care whether you refer to a gene with an NCBI number or an EBI number, as long as it knows, okay? So I now summarize FAIR as the machine knows what I mean. That's the key of what we are trying to achieve. And of course we need machine-actionable units of information for that to have freedom to operate. Oh, I have the same problem as Frank. This is not, okay. So very quickly, back to the original paper that John and I made was, okay, we have this concept in mind. We have all kinds of tokens that refer to it. And then there is sometimes a real object. But let's think about it. If you talk about pancreatic cancer, that is a mental construct. It doesn't exist as in here is pancreatic cancer. You have individual tumors. So some have real life objects that exist in real time. That's the biopsy of the cancer, or anything that exists, you can touch, you can measure. But there is lots of things that are mental constructs that do not exist, like God, you know, doesn't exist in the sense of measurable, but it's a concept for sure. Now, can we represent all these things in machine-readable format, and would that mitigate the fact that AI doesn't exist? We have the first professor here in something that doesn't exist. AI, you know, this is just a machine learning stuff. There is no real intelligence, as Frank showed himself. Nobody can even match the little kid there in the computer science, or in the computer world. How do we ever get there? That computers start to understand much more of near sameness and nuances and those kind of things. That's what my talk will be about. Look, people, when they see a symbol or they have to interpret a symbol in their minds, they have lots of ways to do it. They smell, you know, the big difference we all experience today from Zoom is we're here physically. There's a lot more than just, you know, but machines don't have it. Of course, they can get bit sequences in via camera or microphone or whatever, but they don't have this context. But I don't have to spend much time here because Frank gave a very beautiful example of what that means. Now, humans look at graphical user interfaces. We saw some beautiful things for humans. But as I said before, text narrative is a nightmare for machines, as we have heard from Tobias. And we also saw that when he shows a nanopublication, it's a nightmare for us. And he said we don't even want people to look at it. So RDF is a nightmare for men, and the narrative is a nightmare for machines. We still keep publishing narrative. keeping science in a deadly embrace. So, this is my stupid biology version of a nanopublication. And of course, the blue container was just shown to be a bit more complicated, a super pattern. But essentially it says the subject relates to the object. Let's say malaria is transmitted by mosquitoes, or ivermectin treats COVID, or hydroxychloroquine, even up to the Lancet. Now, today, after a year, finally there is this paper coming out that ivermectin was, again, wrong. You know, but it's all still there in the Lancet and so on, these kinds of crap publications. So how do we get rid of those? So you have this container, it has this globally unique identifier, the publication info and the provenance. Well, that's explained by Tobias, great, I don't have to do it, but how do we move this into being a fair digital object that the machine can understand any component of this? I think we are there, or almost there. Because this is the design of a fair digital object. You have this thing in the middle, it has this identifier, it has separate metadata that say I'm the metadata of this thing, and the nanopublication container says here are my metadata. And these could be 10,000 metadata files. I will show you why. Because the next step now, and which means an incredible thing in science, if you look at the nanopublication here as a nightmare for people, and you move on, you move on to what I would call a cardinal assertion, we published about that as well, it's a very simple step. If you take my old favorite, malaria is transmitted by mosquitoes, that triple, if you do text mining, you find it 10,000 times in PubMed. So it's probably there 20,000 times because you only find half of them. But let's say 10,000 times, okay? It's the same assertion, the same three numbers. But the provenance is different all the time. Who said it, when, which article, and so on. So that cardinal assertion would have 10,000 plus provenance files and publication files. You reduce, if you would mine, and there is a company who did this, Euritos, all databases and the literature, full text, Elsevier, whatever you could get access to. We actually, Frank estimated in 2008 in New York at the Concept Web Alliance meeting that it would be 10 to the 14th triples. You were almost right, give or take, you know, 10 to the 13th or 15th. Small error. So this is not manageable for any computer. If you assume, as we did then, and we were also quite right, that the average redundancy of a cardinal assertion is 1,000, 10,000 for malaria transmitted by mosquitoes, you know, and hydroxychloroquine COVID probably also at more than 1,000 times already in the literature. Everybody starts parroting this stupid thing. So then you would be down to 10 to the 11th, which is already a huge reduction, but still a lot for any machine to deal with, 10 to the 11 triples. However, now we take the next step. So we have the cardinal assertions, they have the same assertion, but you map them to a cardinal assertion, all these nanopublications. And there is this company, Euritos, has cardinal assertions, and they link out to the provenance files, even in a completely different data system, different database format as well, MongoDB. And now, sorry, going one step further, this thing is really playing tricks on me, we construct a noded. And I also remember years ago in Frank's room in Amsterdam, he said, why does it take a stupid biologist to get to this noded thing? Because what we see as a fair digital twin now is you take all the cardinal assertions that have been done about the same subject, let's say malaria, you bring them all together in a file, and that is a new fair digital object because it has its own container, its own GUPRI, and it has its own provenance. And this is everything we ever said about malaria. Now we do this for every gene, for every protein, and everything in the life sciences. We are down to less than 1 million nodeds. Because in the entire PubMed database, we do not publish about more than 1 million concepts. So we go from 10 to the 14th to 10 to the 11th to 10 to the 6th nodeds. And all these nodeds can be depicted in multidimensional space. And then we can do a number of things. This is almost my last slide already. That is almost getting to something that we might call artificial or machine intelligence and could be used in hybrid intelligence. First of all, We have used this for years now, and Eric has several very good papers on it, where we say we can look at conceptual similarity of these knowledge. So we have already brought all genes and all diseases and predicted 120,000 new gene-disease combinations. And we are now going to do this very likely with LAREP for all side effects of drugs. But very importantly, so this is the easy thing. But the other very exciting thing for me is that we can deal with near sameness. So if I have actin in the mouse, a very conserved protein, and actin in humans, their knowledge will be almost identical. But there are at least two differences. There is one of these assertions says occurs in Homo sapiens versus occurs in mouse. And the other one says a gene located on chromosome 3 or on chromosome 14. So if I'm interested in the semantic type, species, and chromosomal location, these two knowledge are nearly identical. So without explicitly telling the computer knows they're basically the same thing. Stronger, and we'll come to the quas later, if we say we are not interested in species and in chromosomal location because I'm just studying the protein, and the crystal form of actin in mouse and human is identical, so you wouldn't know who made it, then basically, if you filter out species and chromosomal location, the two knowledge become exactly identical. So the machines can deal with near sameness and with conceptual drift. Because if this was the knowledge of Donald Trump when he was just a criminal, that had changed a lot over time when he became president, and it probably will soon go back to criminal. But anyway, the point is you can now follow the knowledge over time. And Tobias and Michel Dumontier made this trusty writing to prevent nanopublications from changing, because you hash the content of the container and the hash would change. Here the hash will change, and it's on purpose. So you would always be able to go back to the knowledge as it was 3 weeks ago by time date stamp on all the cardinal assertions. So provenance is exactly what Frank and I were discussing years ago in the linked open data cloud. There is not enough provenance to make it optimally useful. Nanopublications have this provenance, and now we can do quas, because we can filter on time date stamp, on semantic type of the subject, the object, the predicate, whatever. So if I want to look, we now need only one knowledge of water, and it's there in the C data cloud and in 20,000 thesauri. Everybody deals with water. We can make only one knowledge, and if we say, I want to look at seawater, one of those assertions maybe contains mackerel. If it was my drinking water, probably not. So you can filter on, and this is what humans do. This is what happens all the time in your brain. You look at a concept from a certain perspective. You don't use a lot of stuff that is known about that concept. You only see it your way. Oh my God. So just to see how we use this now with Eurytos, here is one example of how we can use this. There is this upcoming epidemic, which is mainly in the United States, but I bet you it's here as well. There was this idea, this is what we call a real-world anecdotal observation, it's not yet proven, that people with heavy overweight and diabetes type 2, frequently associated, get early onset Alzheimer. Imagine all the overweight people in the US not being able to work after 55. It will kill the whole economy. How would that work? Well, you know, we take all the genes involved in this case with the 3 diseases, we look at their overlap, and we say, okay, what you have to look for is how this works. Is there you see the 3 diseases, here you see all the 68 genes that are common to all 3 of them. So if you now superimpose all drugs of which you have the knowledge on this picture, you will have the most likely drugs that could help against the early onset Alzheimer of those people. And this is now what we will do systematically for all drugs and all diseases. We already did it for genes and diseases, so it's essentially the same approach. So I think this is already more or less this is my last slide. 20 seconds to go. You can make a FAIR digital twin of a person, of a molecule. We could make the FAIR digital twin of 230 billion spike protein variants that Eric can predict with the computer to emerge in the coming years. and then start studying them. So one big project we're involved in is that MedTech NL, where we want to make a fair digital twin of every Dutch person from echo to grave and export quas of this thing for research into a research environment. That's the future of scientific publishing, and forget papers. We have to publish data with a supplementary article. Yeah? I don't say we shouldn't publish articles anymore, but the article should be supplementary to the paper, not the other way around. Thank you.